The chemical engineer often needs to separate mixtures of materials. These mixtures sometimes occur naturally. Petroleum, for example, is a mixture of a great many chemicals. Some mixtures occur as a result of chemical reaction. Few reactions will produce a single pure chemical. Often the desired material is produced with some that are undesirable. The resulting mixtures must be separated so as to recover the wanted one in as pure a state as possible. Distillation has been used to separate mixtures of liquids since the earliest days of chemistry. It is based on the principle that if a mixture of liquids is heated, some of the ingredients will evaporate faster than others, and this property can be used to effect a separation. Let us imagine that we have a mixture of two liquids, A and B. In equal parts, the mixture contains 50% of liquid A and 50% of liquid B. If we heat the mixture until it boils, we may find that the vapor contains 75% of liquid A and only 25% of liquid B. Liquid A is evaporating faster than liquid B. In distillation, a liquid mixture is heated until it vaporizes, and the vapor is then condensed back into a liquid. Two liquids are generally quite easy to separate by distillation if the pure materials have boiling points that differ by a considerable amount. But modern techniques permit the separation of liquids whose boiling points are close together. Separation of mixtures of two liquids is called binary distillation.
Distillation can be carried out as a batch process. This was the original kind of distillation and is still sometimes done today. For example, alcoholic beverages such as brandy and some whiskeys are distilled by batch processes. Essentially, these distillations consist of separating ethyl alcohol from water. Consequently, there are binary distillations. However, continuous distillation is faster and more efficient than the batch process. And most modern stills are the continuous type. Continuous stills are called distillation column, figure 8.1, because they look like circular architectural columns or large diameter pipe standing vertically on one end. As shown in figure 8.2, the tray is covered with a layer of liquid. The lower edges of the bubble caps are below the surface of the liquid. Vapor rising in the column comes up under the bubble cap and is forced to bubble through the pool of liquid on the tray, thereby thoroughly mixing the vapor and the liquid. The liquid on the tray is cooler than the rising vapor. As the vapor bubbles through the liquid, any material in the vapor that is close to its condensation point, i.e. a temperature identical to its boiling point, will tend to condense and remain in the pool of liquid. At the same time, the vapor in cooling is heating the liquid. Any component in the liquid that is near its boiling point tends to vaporize and be carried up the column. A temperature gradient occurs along the height of the column, with the highest temperature at the bottom near the reboiler and the lowest at the top of the column near the condenser. After the column has been in operation for a time, the components of the mixture being distilled tend to distribute themselves on the various trays of the column according to their boiling points. The materials with the lowest boiling points will be near the top.
Once the column is working, feed can be continuously introduced, usually near the middle, and product withdrawn from the top of the column, from the bottom, and at various intermediate points. If the material being distilled contains only two components, such as ethyl alcohol and water, all of the desired product, the alcohol, will be taken from the top of the column. This is called overhead product, or simply overhead. The water, which is unwanted, is taken from the bottom of the still and discarded. This is called bottom product or bottoms. If the material being distilled contains many components, as is the case with petroleum, products of desired composition may be withdrawn from intermediate trays as well as from the top and bottom of the still. This is known as multi-component distillation. Figure 8.3. The product withdrawn from intermediate trays may not be pure. It may be a mixture of several liquids with boiling points close together. Note that in petroleum distillation the bottoms are not thrown away, as was the case in the water or alcohol distillation, but are themselves valuable products. When the product withdrawn from one of the plates of a still is a mixture, it may be sellable as such. Kerosene and gasoline are such mixtures. However, if desired, the mixtures may be further separated in another style.
The liquid returned to the distillation from the overhead condenser is known as reflux. See figure 8.1. In general, the more overhead returned to the column as reflux, the better the separation between the components of the feed. The ratio between the amount of overheads taken as product and the amount of condensate returned as reflux is known as the reflux ratio. Columns can be designed to operate at high or low reflux ratios. Obviously, a low reflux ratio is desirable because more of the condensate can be taken as product. But a column designed for this must be quite tall with a large number of trays. It will therefore be very expensive. If a high reflux ratio is used, the column can be shorter and less expensive. However, high reflux means that more heat must be introduced into the reboiler to revaporize the reflux. Thus, although the initial cost of the column is lower, the operating cost for extra fuel will be higher. It is the job of the design engineer to balance the high initial cost of the tall column against the higher operating cost of the shorter one, and arrive at a compromise that will have the lowest total cost over the life of the column. Another kind of separation that uses heat is the concentration of a solution of some material, often a salt, in a liquid. Most often the solvent is water, and the concentration is accomplished by boiling the solution so that the water turns into a vapor and is removed. The equipment in which the solution is boiled and concentrated is known as evaporator. In evaporation, what remains after the liquid is boiled off is the desired product. The vapor has no value and is discarded. In distillation, the vapor is usually a valued product. Another difference between distillation and evaporation is that there is never any attempt to separate the components of the vapor.
An evaporator is a special kind of heat exchanger, usually vertical. Heating is usually done with low pressure steam. The vapor leaving the evaporator may be condensed, creating a vacuum in the evaporator. The effect of the vacuum is to make the liquid in the evaporator boil faster and at lower temperature. Sugar solutions are usually concentrated in such evaporator. Although the vapor from an evaporator is an unwanted material, it does have some value because it contains heat. It is possible to use the hot vapor to heat the contents of a second evaporator. Sometimes vapor from the second evaporator can be used to heat a third one, and so on. This series of evaporators are known as multiple effect evaporators and have the advantage of making more efficient use of the heat in the steam than is possible with a single evaporator. Multiple effect evaporators with as many as 4 stages are common.